Welcome to lecture 3 of whatever this course number is, Graduate Probabilistic Programming. I'm still Frank, and today we're going to review graphical models and sort of start some of the actual material in the course. So quick show of hands, how many of you are already familiar with graphical models, know what they are, know how to manipulate them? A lot of people are waving, half, something like that. Okay. We need to know about them, and we'll just have a nice, slow, easy lecture for those of you who already know them, and for those of you who don't know them, well, it'll be too fast. So we'll fit right in the middle somehow. Also, just as a quick poll, I've thought, just to keep things entertaining, that perhaps one or another of the lectures sometime this term I could either do with a Southern accent or with an English accent or something like that, just for the fun of it. So if you get bored and you want me to switch accents, I can. Anyway. So, I mean, we're going to be doing probabilistic programming. And please, actually, I should also say that a huge number of people have been apparently scared away already. Russian, please. Я не знаю русский язык. Sorry, it's not going to happen. Southern Frank, I can do Southern Frank, don't worry. Scottish, not so well. So a huge number of people have dropped the class, apparently already scared off. Maybe they looked at homework 1 and said, I don't like that, or maybe it's personal, don't know. So we can be much more interactive, almost like a real class, because I can see basically everyone who has turned on their camera as requested and isn't terribly backlit. There we go. All right, cool. So ask questions, you know, we might even drive away enough people that will actually even be able to leave our microphones on. I have low expectations of being able to do that, but you know, just at this point, you should just be able to pop in audio-wise in addition to the chat channel and just ask questions as they come. So today we're going to do graphical models. So very quickly, there's a whole bunch of terminology that we can worry about if we want to. It's going to become apparent later on in the term that these are all kind of part and parcel of the same thing when you think in terms of graphical models, but you will have heard terms like supervised machine learning or unsupervised machine learning. In supervised machine learning, usually you have input-output pairs of some kind, which means you can frame things as a regression or classification problem, or you can think about doing some sort of conditional density estimation. That's kind of what supervised learning means. Usually you need training pairs, input-outputs, and oftentimes, because you're not modeling the distribution of the inputs, it's easier in some weird senses. Unsupervised machine learning, it's like dimensionality reduction or joint density estimation. It requires data plus a model. Really, you're not like modeling an input-output pair, you're just modeling data, as it were. It's often harder because you're really leaning heavily on the model structure as opposed to regression or classification. You have to model the inputs. It does give rise to richer models. You can do more things with them. One way of thinking about what supervised learning is, and hopefully this will become apparent when we think about graphical models or when you absorb them through the course of this course, is that many supervised models arrive from conditioning unsupervised models on unobserved data. So conditioning on observed data is going to be like fixing the values of some variables on joint distribution. And the nice thing is that when we move to inference, which we will do starting Thursday, is that when we cast things as inference in graphical models or probabilistic programs, then the techniques that we develop for inference for unsupervised models work just as well for supervised models, so on and so forth. So this is really part 1 of the course, which is not one that I normally stuck in. And actually, this is the unsupervised machine learning course from Oxford. It comes fast and furious. They do all of unsupervised machine learning and graphical models and inference in 4 lectures. So that's what you're going to get. You're going to get the old Oxford treatment, and then we can go on to probabilistic programming. So the learning goals for this first part, and really corresponding to the first homework, are to understand the connection between this graphical modeling, notation, and so on and so forth, and joint distributions. There's a couple of books that we refer to I will refer to throughout the course. This one in particular, you can see its spine is well used, but Pattern Recognition Machine Learning by Chris Bishop is a little bit dated now, but it's still, I think, the most elegantly written. And then an ex-UBC prof, both of whom are good friends of mine, but Kevin Murphy's Machine Learning, A Probabilistic Perspective has all the good stuff that you could possibly want in it. And if you're going to be a machine learning person or pretend to be a machine learning person in the future, I highly recommend that you just go ahead and buy these books and read them. So those are the Bishop and Murphy references here. That worked, yeah, good. We would like you to be able to invent graphical models for problems of interest. That takes a little while, and the whole point of probabilistic programming is I want you to think in terms of programs rather than graphical models. But in the second part of the course, you'll see that there is a language or family of languages that, in terms of denotation, correspond to graphical models. So you don't necessarily have to think in terms of graphical model formalism. You'll be able to think in terms of programming language formalism, and that's one of the big advantages of probabilistic programming. But in the context of graphical models, and it makes sense to start going over at least one time sampling techniques or inference techniques, in particular basic sampling techniques. And in part one, we'll talk about Markov chain Monte Carlo in particular, and talk about Metropolis Hastings and Gibbs sampling, so on and so forth. Sort of as stochastic gradient descent and gradient descent is for continuous optimization, Metropolis Hastings, Gibbs, Markov chain Monte Carlo are the workhorses of general purpose inference. So we'll cover those in part one. We won't talk too much about conjugacy. I'll explain what it is and talk about it a little bit, and I think in the next lecture or 2 lectures from now. But you should be aware of it and understand how to exploit it for analytic marginalization, which is something that we'll want to do at various points, or you might want to do for a project even in the probabilistic programming context. You certainly will need to and be able to derive and implement Markov chain Monte Carlo samplers for arbitrary graphical models, because that is, at the end of the day, the primary activity of probabilistic programming systems research and so on and so forth. You'll need to understand Monte Carlo integration, and more importantly, probably at least at this level, is to be able to understand how to formulate inference questions, how to formulate queries in terms of integrals and integration. Conveniently, along with this section, I don't know how many of you have actually looked at this or started reading these the notes corresponding to section 1. How did I know? I just had a feeling. Great. Not many of you have done it, and I would have guessed one of the two that had taken a look at this. That's great. These are really nice lecture notes, and you can read them and really get through. Obviously, as you know, you're all advanced learners, so you know that reading in advance of things is generally makes the learning more efficient and more pleasant. So please consider doing that. And again, there's a bunch of books that you can take a look at. The 2 of which I put in front of you already are the ones that I would most highly recommend for at least this part of the lecture. And Emmanuel, if you want to, and it's appropriate, you could turn on your camera so I can see you too. So what are graphical models? Well, graphical models correspond to a subset of probability models. Graphical models allow you to visualize the structure of a probability model, and they're useful for model design and development, pre-probabilistic programming, and I would argue even still today, they are a language in which one can think. If you haven't thought in such a language, then it'll take a little bit to develop it, but it's the kind of thing that, I didn't draw a graphical model here, but it's the kind of thing that we use to communicate amongst ourselves all the time. We will develop the language of probabilistic programming that is more expressive in a formal sense later on, but it's a way to communicate about modeling assumptions and so on and so forth. For that reason, it's useful for model design and development. And graphical models allow you to encode properties of the distribution that you might care about when doing inference or so on and so forth. Some of those properties you can encode explicitly. Others, in other words, the graphical language encodes them explicitly. Others, you have to run algorithms on the graph or other kinds of inspections, do other kinds of inspections. In particular, conditional independence is something that you can get from a graphical model via inspection. So in other words, you can figure out which parts of the model are independent from what, conditionally independent from another. And maybe most importantly, inference, learning, these all can be formulated in terms of computational operations on the graph. In other words, you can develop generic algorithms that work on any graphical model or are parameterized by a graphical model that you can apply to any problem that you write down in the form of this graphical model. And again, second part of the course will be establishing a language connection between the language and a language or family of languages and graphical models. So what are the graphs of graphical models? Well, there's at least 3 forms of graphical models that are in common use. The one on the left is a directed graphical model. The one in the middle is an undirected graphical model known as a Markov random field, and the one in the center is a Markov random field, and the one on the right over here is known as a factor graph. We will almost exclusively focus on conditional, on Bayes nets or conditional graphical models, directed graphical models. So vertices in graphical models correspond to random variables in the statistics and probability sense. In factor graphs, these little square nodes of a graph correspond to compatibility functions. So these would be random variables here, and there would be functions on these. So again, I will skip this part. You can read about that on your own if you want to. Generally speaking, the random variables have some sort of type in the programming languages sense, and the type system is something like float, int, string, whatever. But then also the probability distribution or density function that governs that is the law for that particular random variable. Okay. Graphical models can represent structured objects like vectors, arrays, distributions, infinite sequences, embedded graphical models, so on and so forth. That will become more apparent when we start dealing more formally with them in terms of computer language. But the point is that either this can be the distribution of a vector. In other words, these could be all the elements of a random vector that happen to be distributed according to some probability model that factorizes according to this graphical model. Or each node itself this could be a vector, this could be a matrix, this could be a string. Or there could be inside of this, and this is more important than you might actually think, this node itself could be actually some graphical model inside. Okay, so these things can be nested. Edges, particularly directed edges, correspond to dependencies. Dependencies. This is not independencies. Okay. Independencies, particularly in directed graphical models, have to be read off in a different way. So the dependencies can be directed or undirected. And the directed ones are usually associated with conditional density functions or conditional distribution functions. And over here, they're usually called something like compatibility functions or potentials. I prefer potentials, but the vision community sometimes talks about compatibility functions. Yeah. So directed graphical models, they have lots of different names. They're known as generative graphical models, generative models, Bayes nets, so on and so forth. Vertices, again, random variables. Do directed edges have to encode causal relationships? Oh, Jason. um, um, I think the answer that I'm going to go with here to be safe is that they usually do, but they need not. Okay. Yeah, that's I'm just going to go with that. So vertices again are random variables. Notably, and this is rather important and sometimes gets overlooked. Notably, this node, for instance, can be Dirac distributed. So if this is x and this is y, we can say that this is, Dirac. Depends on which notation you're used to, x plus y or something like that. Or in statistics notation, it would just be a delta mass or a Dirac mass on the value x plus y. So in other words, these are going to be conditional probabilities, but a Dirac distribution on a deterministically distributed quantity is still a conditional distribution. So deterministic computation graphs are a subset of graphical models. Okay? Edges indicate, well, the link function argument structure, which is more to say that if this is, say, for instance, mu and this is sigma, right, this variable x might be distributed normal mu sigma squared, okay? Note that this edge then hides a deterministic operation, which is the squaring of sigma, okay? And in fact, you can see this normal distribution as being a vector valued function, which takes a vector, mu sigma, and then there is a link function L, which takes that vector and produces a vector, so on and so forth, okay? Fine. So they're good for generative descriptions of data, and as Jason pointed out, often generative descriptions correspond to causal mechanisms, but they don't necessarily need to, and it certainly doesn't. Causal reasoning is very dangerous to think about, because you have to intervene in variables, which means breaking edges and that sort of stuff, and we're not going to talk about that in this course at all. So, so basically, all of the edges that flow down form statements of like if A, then B with some probability, more or less. Okay. Oh, I did miss Emma's question, sorry. Is genetic programming a graphical model or similar to one? No. So genetic programming is an algorithmic procedure for selecting for optimization of discontinuous functions, right? One can describe the computation performed by a genetic optimization algorithm in terms of a flow of random choices. So you could say, I have a population, and there is a graphical model corresponding to, you know, A, B, so on and so forth, and then is this A, and this is A, and so on and so forth. So the value of a random variable in a population selected amongst, you know, a set of precursors or something like that, that the computation flow of a genetic programming algorithm can be expressed as a graphical model. But graphical models are not genetic programs. They're explicitly ways of denoting graphical models, probability distributions, and then we're going to talk about what operations we should perform on probability distributions or want to perform on probability distributions to ask questions. So undirected graphical models are super cool, but again, we're not going to touch them very much in this course. These models are known as Markov random fields or Ising models. Vertices are variables, and the edges are argument structures of energy terms, and they're good for specifying constraints between variables where generative relationships aren't obvious. In other words, neighboring pixel similarity in images, or spin states in ferromagnetic materials, or something like that. In general, you might write a probability density function over something like this. If this is, you know, x1, x2, x3, x4, x5, for instance, you might say that p of x, the vector, is proportional to e to the sum over, this might be, you know, f1, 2, this might be f2, 3, so on and so forth. Sum over ij, pairs of fij of xi, xj, something like that. Okay. So for those of you who have any sort of physics background or something like that, this does not imply a causal relationship at all. It just says that there is some well, these are technically energies up here. There's some set of states that is more probable based on an energy, so on and so forth. The directed graphical dependency graphs for SSA form, and I can see how if else could be implemented to deal with the control flow in this kind of model. Ooh, ooh. Oh, I like it. This is good. Okay, we've got, where's Mia? Okay, there's Mia. Okay, who almost even smiled. Okay, great. Oh, that's beautiful. You obviously have. Are you a programming languages person?
Not really, but I've looked at autodiff stuff before.
Oh, yes. Sweet. Okay, I'll go back to that in just a second, just to finish this up. So you can imagine how multiplying together or adding in the exponent a bunch of potentials and then summing over them in order to compute the normalization constant would allow you to specify the joint probability distribution of a set of particles whose compatibility is indicated by these link functions. Okay, fine. The directed graphs look like the dependency graph for a single static assignment form, and I can see how if else could be implemented to deal with other control flow in this kind of model. Okay. I think the safe thing to do is say, please don't drop the course and stay with us until we actually get to control flow and linking like a first order probabilistic programming language to graphical models. But the idea that assignments made in single static assignment form, which for those of you who don't know what single static assignment form is when you do a compilation pass and so on and so forth, and you keep making variables, so on and so forth, such that every statement is of the form some new variable name gets some operation of earlier variables. I think that's a reasonable, you know, A is, you know, plus 1, 1, and then B is, you know, plus A2, and then C is B plus A plus 3 or whatever. I just switched notation to plus B A, that's fine. A form like this says basically there is a node, right, for every variable, and there's every one of these variables is a fresh variable and it's unique, right? So indeed, a single static assignment form for a program is a directed graphical model in which all of the link functions are deterministic and all the distributions are Dirac. Okay. Okay. If you then put probabilistic statements on there so that you have actual primitives in here that are like sample normal, then indeed you have something very close to a probabilistic programming system already in the forward direction. So in the simulator, you have a probabilistic simulator. You don't have something that does inference. So the hard part is doing the inference part. Cool. Other questions, comments? That was honestly maybe the most awesome early question in this course, or a course like this I've ever gotten. So the standard is embarrassingly high at this point, so keep going. Cool. Yeah, so factor graphs are a generalization of undirected and directed graphical models. Vertices are there are two sets. Is a bipartite graph, meaning you can separate out the circles from the squares, and you could equivalently write a factor graph, and you can always do this in this kind of this kind of form where there's two parts to the graph, and you can cut the graph in half by to separate the circles and squares. Circles are random variables again. Squares are compatibility functions. It's a more explicit representation of Markov random fields. You could write a Markov random field in exactly the same way. It's so on and so forth. Same thing. Factor graphs are really a very nice notation and formalism for writing down and thinking about message passing inference algorithms, which also we won't worry about too much in this course. But if you have implemented or heard of belief propagation or expectation propagation or something like that, there are probabilistic programming systems that work in factor graph formalisms and develop general purpose inference algorithms using factor graphs. Again, that's not what we're going to cover. So, generative models of joint distributions. So let's think about arbitrary joint distributions over three variables, A, B, and C, and recall that you can decompose joint distribution in the following way. So you've got the joint distribution of ABC. You can factorize that as the conditional probability of C given AB times the marginal probability or joint probability of P and A and B. And then you can break down P of A and B again into the conditional probability of B given A and A. Okay. So this decomposition always holds. Okay. And you can there's even a name for this. I always forget what it's called. What is this called?
Do you mean the chain rule for conditional probability?
Yeah. The complete factorization, who knows, whatever. I'll refer to this as a complete factorization or something like that. Okay, so what does this look like in terms of a graphical model, just for the fun of it? So we have C given A and B, and we have P of B given A and P of A, okay? Fine, so that's what the graphical model looks like for this. Obviously, the directions of these edges can be moved around so long as they're directed. So long as you have a complete set of edges, then you have a full description of the joint distribution, right? Note that this also, and this is why we think about this as, and we call these generative models, having a factorization that looks like this gives us a scheme for generating samples from this joint distribution, right? Anybody want to say how one would go about doing that?
Sample A, then sample B, then sample C.
Sample A, then sample B, then sample C. That's right. Okay. So also, and this is fast and furious, but also the thing that we need to care about is that if you drop edges, in other words, if you drop conditioning, then this is no longer a complete factorization of the joint distribution, right? And it corresponds to a less expressive model, right? Okay. There's fewer parameters. There's, it's a less expressive model, basically. Okay. And we could go into lots of details about that, but it's it's a grad level course, so we're going to go relatively high level here. Okay. The graphical representation and the actual factorization of the joint are directly translatable from one another, right? So we have some vector here, p of x, consisting of x1 to x7. And you can basically pick off the terms here. So there's this term, there's this term, there's this term, there's this term, so on and so forth, right? This is not a complete factorization, right? It's not it's not x1, x2, given x1, p of x, x3, given x2, x1, so on and so forth, all the way up to p of x7. Given there's lots of missing edges, which means that you're making all sorts of simplifying assumptions about the probability distribution, right? So, but in general, when you go back and forth, there's a term for every vertex, and the variables that are the arguments to each variable's link functions are connected via inbound edges. So in math, and we'll refer to for every particular variable k, xk, its parents, the link function as f of the parents of A. So the parents of x5 are x3 and x1 here. Okay, fine. Does that graph indicate x1, x2, and x3 are not dependent on the others? Good question. Wonderful, thank you. I'm going to count on you to be the honest voice of everyone who has no freaking clue about what's going on, but is too embarrassed or afraid to ask. So stay strong, Emma. I was that person when I was in grad school, so please stay strong. Yes. Okay. So it does not mean that they're independent. Not at all. Okay, and this will become more apparent later on, but yeah, it again. I don't even know if I don't know what I have next. Let's do something just for the fun of it. So an even easier probability distribution, I'm just going to write in the margins here. Okay, so there are some conditions in which A and B are independent. Okay, and we're not going to go through this. I expect you to read this on your own. It's in the lecture notes. It's elsewhere, but let's look at this. So if we don't know the value of C, right? What are A and B? Or what's the relationship between A and B? Well, we can look at this and say, okay, if we don't know the value of C, we can integrate it out, right? So the integral of P A B C is the integral of this P of C given A B is equal to times P of A times P of B, right? DC, and I should say DC here. Great. These are independent of C, so they come out, and if you integrate this over C, it's 1. So this is just equal to P of A times P of B, okay? So if you don't know C, then A and B are independent. What if you do know C? We haven't talked about shading yet, but what if you do know C?
So is it like saying then, it's like if you don't know C, you're saying like A and B define what C is, but if you've assigned C something beforehand, then
So your
C...
question was about dependence, right? So the
Yes.
question is, so what does dependence mean? So dependence is whether or not the joint distribution of a set of random variables factorizes as independent. In other words, you can make independent choices about their values, and the probability of those independent choices is equal to the product of the probabilities, right? If they're dependent, then you can't decouple the variables in that kind of a way. So your question about whether or not x1, x2, and x3 are dependent or independent require actual operations on the graph. You actually have to study the graph, and it depends on whether or not variables are observed or not. Okay, so it's the story on this is a little bit is a little bit is a little bit more how do you say, subtle, right? So the quick answer to your question is, if in this graph they are everything is unobserved, then yes, you make independent choices for x1, x2, and x3. But if you condition on, or you happen to know the value of x6, then the values of x1, x2, and x3 become dependent on one another. Okay, so this is the description of the joint distribution. Okay. Okay. Is that clear enough, or do I need to do more? I'm looking for faces. Everybody looks bored, horrified. Okay. So here's a quick question, and this is a fun one, right? So if we go back to this, if we just look at this graphical model, right, which corresponds to this particular joint distribution here, this one, right? If every one of these is a proper conditional probability distribution, what value does this take if you integrate over the entire domain of X? I think I saw Adam indicate an answer. Jason indicated an answer. Okay, 1. Everybody comfortable with that? Okay. The idea is, of course, that you can move this integral in to the 7, remove the 7. You can move this integral in to the 6, remove the 6, so on and so forth. Everything goes away. Okay. This is going to show up. This very quick thing we just talked about here is going to show up when we talk about auxiliary variables at some point. And will show up when you're thinking about how to, in some circumstances, how to make efficient samplers for various models. Which is to say that anytime you have downwards connections in a graphical model, you can always marginalize out the variable by just forgetting it. Okay. Fine. Okay. So there's some other notational shorthand that we use for products and constants. Squares, or otherwise known as plates, indicate multiplied replication. Filled circles indicate observed variables. Small dots or no dots indicate fixed quantities, which we'll call parameters or hyperparameters, or they're all kind of the same thing. In math, this particular graphical model corresponds to this factorization of a joint distribution. Okay, so here we have a vector of t's, we have a vector of x's, we have some sigma squared quantity alpha w, and there are n random variables in the plate. There's the product over n of a bunch of conditional probabilities. Note that these arrows connect to all of the children. Okay, all right, fine, cool. So a graphical model is not very interesting in and of itself until you actually make a determination of what these probabilities are, right? What are the types, what are the density functions that govern these variables, so on and so forth. So you have to specify the conditional densities, right? So if we make the following assignments, right, of, if we say that W, which is some vector quantity given some hyperparameter value alpha here, is the product over the dimensions of W of a univariate normal with mean 0 and parameter alpha, which is the same thing as saying multivariate normal with mean vector 0 and covariance alpha times I, and Tn, which Bishop refers to as a target or whatever, given W and Xn, which Xn is also going to be a vector, and sigma squared is normal W transpose Xn sigma squared. Then now we have a fully specified probability model, right? So we know from before that we need to take that the joint distribution of all of the variables in this graphical model is the product over n of this these conditional probabilities and this conditional probability over W. Now we make particular choices about two things. One, the link function, which tells you how to go from the arguments to this particular probability distribution to the values that are used in the distribution itself, and the distribution. The distribution, generally speaking, specifies the type of the random variable, right? So again, in this type system sense of, is this float or whatever, this, whoa, what happened there? This is, of course, going to be a real value. You know, Tn will live in R, right? And W will live in R to the D. Okay. Now, Jason asked if we're doing MLE with respect to alpha, would alpha still be a small dot? So there's some, yeah, okay, fine. So in the stuff we're talking about right now, we're not going to be talking about maximum, and in fact, for the first part of the course, most of the course, in fact, we're not going to talk about maximum likelihood at all. We're going to frame everything as inference, just to keep things simple, okay? So any of these are constants. They're fixed. We're not messing around with them, okay? They're given. And if we wanted to learn alpha, for instance, we would instead replace that with make alpha a random variable and put some constant hyperparameters on it. Okay. This is again where maximum likelihood or parameter learning or learning in general can be framed as inference by just lifting the prior one level higher and asking for the posterior distribution over, in this particular case, alpha. Make sense? Naomi, awesome. Well, I'm gonna try to, oh, there's Naomi. Okay, great. Awesome. Quiz. You've asked the first quiz question. So to what well-known model does this correspond? Okay. Awesome. Okay, so we've got linear regression, OLS, which stands for ordinary least squares, linear regression, so on and so forth. Okay, so this model says we have, yeah, what the heck? I'll go crazy. Okay, we have x1 and x2, and x in it will be some vector x1, x2, but we just have 2 dimensions for now, so this will have some value, so x1, so this might, yeah, I should not do that. This is d1, d2, these are the dimensions of x, and we're going to have some x values and some t values for all of these inputs. So in other words, where you are in the xy plane, there's going to be some corresponding t value, so on and so forth. And we're going to, and W is going to describe a plane. And this normal term accounts for deviations away from the predicted plane to the target data. And W transpose X is, in fact, the value of the plane. Okay. Cool. Is this a L2 linear regression with L2 loss and norm? For somebody who's taken 340, absolutely. Yes, that is what this is. Is this a supervised or unsupervised model? Okay, 1 vote for unsupervised, 1 vote for supervised. Supervised. We should really have some, I should really know how to use the voting clicker thingies, however they work. Do people actually use clickers in these courses, online courses?
You can set up polls.
Yeah, but that requires work in advance. The polls are great. Is that what you said, Ryan? Polling. How do I do it? I've never done a poll. Okay, ask a question. Let's, oh my goodness. Oh, no. No, not happening. There's too few people for that. So I was kind of hoping for the answer, it doesn't matter. Okay, it's a graphical model. Some of the variables are observed, some of them are unobserved. What's the question that we would like to answer here, given this graphical model? If we just look at this graphical model. Not how can we find W? I think that's not a great answer here, Ryan. I don't mean to be overtly critical, but good try, Ryan. Let's can you rephrase that to be something better? How can we infer W? Close. Keep going. One more try. The value of t for new x's, that's a good one, but there's no graphical model node for any new value of t. Right? How do we infer the, are you going to do one more try or not, Ryan? What if we change W? Okay, yeah, so great. So what I'm going for is the posterior distribution over W. That's what we care about. We care about the distribution of W that explains the data well. Okay, so when you have observed data and you have unobserved data, you can look at the graphical model and immediately know what kinds of questions that you can ask and how you, and what's of interest, because the things that you don't know aren't filled in, and you want to know something about those. Generally speaking, we're going to ask to characterize the distribution over those things. And when we're conditioning on something, thanks to Bayes' rule, that means the posterior distribution over something. Not a point estimate, so on and so forth. Okay. So it's something that, you'll have to forgive me for the moment, because you'll find out later on that we actually still do parameter estimation, and we do maximum likelihood and these sorts of things, and we do often in practice actually think about parameters separately from things that we integrate over. But for now, I want us to all actually just at least acknowledge the fact that inference and learning and prediction, they're all the same thing in this graphical modeling framework. Okay, so what Jason talked about in terms of learning a value of alpha, which we haven't talked about, which would involve integrating over W and maximizing with respect to alpha, that sort of thing. We can learn a posterior distribution over alpha just as well by making it an unobserved variable and trying to characterize its posterior distribution. Okay, so parameter learning can be framed as inference by just lifting one level. Prediction, what Naomi, I believe, talked about, can be framed as inference. Usually is framed as inference, actually. Of course, inference is inference, right? So one goal is the posterior distribution of parameters. I shouldn't have written here. Of latent variables is what I should have written here. Sorry. Given data, and there's only one latent variable in this model. It's W, given whatever we observe, and that's all of the T's. Okay, and we know from Bayes' rule that we can write this down, and this also is another thing that you should just have in your head straight away. Every conditional distribution of interest is proportional to the joint distribution. And what is the joint distribution? You can just read it off of the graphical model. Okay. All that's missing is some normalization constant, right? Which in this particular case is going to be a function of T. Okay. And often, notationally, just so you get used to it and so you don't get tripped up when I start writing crazy stuff on the board like I did the other day and so on and so forth, usually we'll just drop fixed quantities because they appear on the conditioning side of all the equations. Basically, if everything, you can put an A here and given A here and an A here, and it doesn't matter. Everything still holds, right? So, why is this a proportionality? Again, right? I mean, I don't want to belabor this point, but it's Bayes' rule. You need to be able to do that like in your sleep, right? Fine. So why is it proportionality? And maybe the more important thing is what should we do? And Emma wasn't so far off here, although I might rephrase what she wrote as well, right? So why do we want the posterior distribution over W, right? And most of us have seen linear regression. Many of us haven't necessarily seen a Bayesian treatment of linear regression, but why would we want P of W given T? And I'll go back to my amazingly awesome drawing and maybe make it even simpler and just talk about a 1D case, right? So we've got some input data. These are going to be our x's. So this is going to be x, and this is going to be t. That's not a lambda, that's an x, and this is going to be t, right? We've got some data, and we have some regression that's parameterized by W, right? So what does P of W given T give you? What is it? And I know it's silly that we're going really slow right now, or maybe it isn't, I don't know. But understanding this, what the value of the posterior is really important if you're going to understand, like, go with us on this journey with probabilistic programming. So what's the point of having the posterior distribution over W? What is it? I'm looking for chat or audio or anything. Or just think for a little while, and I'll continue to blather on and make it hard for you to think. Ah, the uncomfortable Zoom silence. Prediction modeling nature uncertain. Ryan has thrown the kitchen sink at us, okay? 42! No. So the posterior distribution over W in a ordinary least squares linear regression, Bayesian linear regression, think, well, W corresponds to the description of the plane, the line, whatever, and a posterior distribution over W is going to give you a distribution over lines or regression surfaces that match the data. It's going to be a restriction of the prior, which we specified here as being normal about alpha I. In other words, there could be lines that go like this and like this and like this, so on and so forth, and it's going to restrict the set of possible lines into a subset of model space that well matches the data, but is still uncertain because we don't have an infinite amount of data and we can't drive the estimate to a point, right? Okay. Why would we want a posterior distribution over the line? And this is going to relate to Naomi's point, so I'm giving you a hint. Can we pick the best line somehow? Picking the best line would correspond to maximum a posteriori estimation. Okay, so picking the best line, you can do that. Yeah, if you're weak. Just kidding. No, so we don't want to do that. I mean, you might want to. Totally reasonable, but if the data changes, no. So we're gonna. This is great. So we're gonna keep the data. We have the data. We're given the data. We've got input output pairs. We've got them. That's it. We've got our input output pairs. That's our data right there. We've gone off and measured, right? Okay. What should we predict over here? So those of you who have taken an intro machine learning course, which is sort of a prerequisite for this, like would know that maximum likelihood, there's some problems, right? You're not going to regularize. So Bayesian inference is like regularizing, so you want to regularize, right? So so map is going to give you one line, and then you're going to make a prediction. Are you confident about that prediction? Are you sure? Let's see. Where's Adam? I don't even know Adam. There's somebody here that doesn't have a camera on. No. Or is your camera on, Adam?
My camera's on.
Where are you? I can't see you. Wave or something. Oh, there. That Adam. Yeah. Okay. Great. So Adam essentially gives you is right. Okay. So I'll just graphically do it again. So if you have one line, if you just have a posterior distribution, if you have map, if you have MLE or map, which are going to be one line, you're going to get one regression surface, and then you have the likelihood term right here, which would give you a little distributional bump around this, right? But that uncertainty is actually not properly calibrated under your model because actually you're uncertain about what the line is. Okay, and every single one of these will have a little likelihood bump around it. Okay, and the actual uncertainty that you should report when you're extrapolating something like that is the full likelihood integrated over the posterior uncertainty, which means that actually your confidence intervals, your properly calibrated confidence intervals for out of sample prediction need to be integrated over the posterior distribution if you're going to do it right. Okay. Okay. So, and Adam's point is exactly right. Jason, did you say no, or is that no, like Luke is falling down the central hole in the What's the no for? We can't hear you.
You said, are you confident? So I said no.
You're such a lovely man. Anyway, okay. So, great. So Naomi's goal of doing out-of-sample predictions, or predicting the next value for some new value of x. Here's a new value of x, right? So I was going to ask you how to do this in the graphical model. So how do we do this in a graphical model, right? Well, this is what the graphical model of out-of-sample prediction, right? So we have all of our training data. They're given. There are the x's here. We have our training data targets, right? But what we don't have is the value for x hat. So we've got x1, x2, x3, and t1, t2, t3, and now we have x hat. Okay, great. Fine. So we already know, well, what did I say? Well, we have to actually, every time we put a node in, we have to say how it's distributed. We'll just say that it's distributed in the same way. It has exactly the same likelihood as before, right? It's just x hat here. So we have a link function for x hat, for t hat, excuse me, right? So where is t hat? Okay. Well, what is it? And this is what Adam put in the chat. So to make a prediction about a new quantity, well, what don't we know? Look at the graphical model. We don't know w, and we don't know t hat, right? Okay. All right. So that means we can look at the graphical model and say, okay, well, we want the conditional probability of the thing that we want, but that's actually a marginal of the full joint, right? Fine. And dropping a bunch of constants over here, what you do is you say, okay, well, if you had w, right, then it's very easy to say what the distribution of t hat is, right? Because we know its distributional form. It's normal, right? Okay, that's cool, but if we're going to marginalize this joint posterior distribution, then we just need this posterior distribution over w given t and everything else. And then we integrate over that. Okay. So, questions, just to make sure that we're all on the same page and we know what's going on. How do you compute this integral? I know that we have some math PhDs here, so, you know, we just hand it to them. That's what I do. You know what really sucks about Zoom is the only thing that I'm good at as a lecturer is actually getting people to interact and learn together. And this is just tough. So we got to work together. We can do this. I'll start calling.
At this point, everything is still Gaussian, right? Is that right, or did I miss something?
Everything is still Gaussian. Yep.
So a little bit of pen and paper. I think we could do it.
Okay, so Baron says, now I'm a physicist, a post-PhD physicist. Gaussians, no problem, I got it. Okay, I'm a lazy ass machine learning person, and I say, you know what? Everything I know about Gaussians is right here.
Yeah, oh, sure. You grab the back of some book and you look at
exactly.
You look it
So
up.
I know that, you know, cool. I know that there's Bayes' rule for Gaussians, so I can just, like, you know, Gaussians happen to be closed under marginalization, conditioning, so on and so forth. I look it up and do it. Okay. Cool. Let's pretend for a second. Let me screw you up. Now what do we do? Am I allowed to do that as well? Is that cool? I don't know. Yeah. Estimate Wolfram alpha Monte. Okay. Estimate. What does estimate mean, Ina?
Well, I guess like it's more like sample. You sample and then you do the integral, but it's not really an integral. I don't know.
Okay, so you're saying basically if you could get W from P of W given T somehow, then this thing you could do is 1 over K of P of
Yeah.
T hat
Yeah,
given
and distance estimate. Like
W
you don't take the actual integral.
K X hat. Yeah, okay. So this is what we would call a Monte Carlo integral, right? Integral approximation, right? Or estimation, right? Cool. We can do that. I like that. That's totally cool. How do we get this? I can see your fingers right on top of the space bar. You might as well just press it and go. Come on out there. Greg? Okay, cool. So we're going to spend a lot of time talking about how to get that. Okay, like it's drawing samples from a posterior distribution or a conditional distribution is largely the first 2 sections of this course. Okay, and generic algorithms for doing it. Okay, cool. And again, I think I hope at least pictorially in this particular case, it's relatively clear what it means to integrate out W, right? It means that when you do predictive inference, right? When you make a prediction, your confidence intervals, and in fact, the distribution of predicted values that you make will be properly calibrated under the model, okay? And if you don't integrate over W, then your predictions will be overly confident. And that's, in some situations, really, really bad. Cool. Awesome. So I think this is a reasonable time for the Emma Hansen Memorial P break. So if you want to come back at 4:45 or thereabouts, I'll be here. I'll pause the recording. Okay, welcome back. So the remainder of this lecture is kind of, we can either be done super, super fast, or we can engage and have a bit of a discussion, right? Before we go into the mechanics of how to do posterior sampling and so on and so forth, what I like to do is at least put a few graphical models in front of people so that they so that you get comfortable thinking about what kinds of models, models you might have heard of and their graphical model correspondence, and think, get started thinking probabilistically about a number of things. So we'll start with a model called the hidden Markov model. How many of you know hidden Markov models? A few, sort of, maybe. Okay. So a hidden Markov model is the absolute workhorse of probabilistic programming. So you should be comfortable with it. And not to put too fine a point on it, but it really it describes the world model necessary for any AI agent. It describes the evolution of the universe, particle systems, so on and so forth. It is a very, very general modeling framework. The key idea is that you have some observable space. So generally speaking, this is the arrow of time in this direction, although it need not necessarily be time. And you have some observable space. So xn is going to live in some space. Don't know what it happens to be. We should think about what I'd like you to do is think about some applications with me, so you can think about the kinds of inference things that we want to do, and we'll think about what an HMM is and how it can be used. So x is going to live in some space. Let's say, just for the fun of it, to try to give you a sense of how you might think about this, we could think about, and Baron will laugh at this, at my physics naivete. We can think about a particle system bouncing around in some kind of closed container, right? And maybe what you get to do is you get to occasionally, at every instantaneous or in some time interval, you get to observe how many times each wall was hit. Okay. So x then would be, z6. So 6 integers. You get, however many counts, right? The latent state of this system, the latent state of this world, z would be equal to, I don't know, how many variables do you need to describe the position and velocity of a particle in 3 space?
6, right?
I hope that it came up that I wrote it before you actually said it, but if it didn't, I'll give you credit for it. So 6 times n, okay? So we've got little, velocity vectors for each of these particles, and they're running around, okay? Fine. For instance, right? More commonly, you might have the lazy white dog jumped, something like that, okay? So xn might be in some very large vocabulary, and we'll denote that by sigma, which is, isomorphic to the positive integers restricted or whatever, it doesn't really matter, 0, 1 to 5,000. You have 5,000 different words, something like that. And z would live in, I'll make it p, which is going to be the parts of speech, verb, adverb, so on and so forth, something like that. Okay. In this latter application of a hidden Markov model, we can write down a probability model or link functions for a model of, for instance, text or sentences, which looks like the following. So Zn, given Zn minus 1, and some transition matrix A, if you make Z actually not live in 0, 1 vectors, so in other words, if you have 5 parts of speech, you can do a 1-hot encoding, right? Such that Z lives in a space that looks like that for, verb, adverb, whatever. We have this matrix A, which describes how likely it is to transition from one latent state to another. Okay. So I guess we'll just do, I'll guess J, K, and in AJK, AJK is the probability of going from whatever the state is at time step J to whatever the state is at time step N. Okay. And if these are 0, 1 vectors, then the probability that this is basically just going to index into the matrix A. Okay. There will be some initial distribution pi over the first states. Say there are, again, k states, and this was just going to index into the vector pi, and there'll be some likelihood in this particular case with z and k equals 1. Then this will look up the distribution for the kth state and build an observation from f, whatever that distribution is. Okay. So since I was looking at the thing, my iPad, I can't tell whether or not people understand what's going on here or get an idea of what's going on. So I'm going to ask a bunch of questions. So relative to the earlier notation, what edges and arrows are missing from this graphical model? From Zi, arrows from Zi to Z3. Okay. No. Okay, great. So I would say that there are some parameters that are missing. So A is this matrix, which governs not this one, but this one, and this one, and this one. And there's a pi, which is a parameter which governs this. And there is a set of thetas, which connect to all of these. Okay. So again, without going into a huge amount of detail, and it doesn't even really matter what these are, just that there is some conditional probability of transitioning from one latent state to the next, and some probability of producing a particular output given that you're in a particular latent state. What inference objectives might you want to accomplish in a model like this? What's the point? What are you what would you use a hidden Markov model for? I've given you a couple example applications, or rather, give me some other example applications where a hidden Markov model would apply. And people from my group, don't be shy here. That's totally fine. Given a sequence x1 to xn, how likely is this sequence? Okay, great, awesome. So cool. That's a good example. So you have a sequence of x1 to xn. So how would you compute the probability of a sequence in this model, Adam?
Let me just think about it. Well, you could calculate the probability of x1 given your initial probabilities and your choice of A. And then you could condition on x1 to compute the probability of seeing x2 and x1 and so forth.
There's a marginal probability there. So in order to compute the probability of a sequence, you have to average over the latent variables. Okay, so that's even worse than inference. So we'll leave that one aside for just a second. Although it's true, sum out the z's, right? Robot localization, okay. Yeah, so let's, Namrata, do you want to explain how that works to everybody else? I can explain as well, but it would be awesome if you did. That would be cool.
So I think HMMs are used in like Kalman filters, where you have the robot observes like its environment, and we actually want to know the latent variable is where the robot is located. So its observations are dependent on where its actual state is. So we want to predict, estimate the actual state given it's observed.
Okay, so if we're going to do that, let's see if I can. I thought there was a way. So if instead of these, if we're doing robot localization, what would we have? What's latent?
The state of the robot.
You talked about robot localization, so that's cool. Let's go with robot localization. What do you mean by the state of the robot?
Say the position and velocity.
Cool. Okay, so Z in will be position and velocity of robot. But don't you just know that?
What we know is actually what we read from the sensors, which can be noisy.
Okay, and what might you sense? I just want to make it. I want to get it so that everybody is. What might you sense? So you've got a robot. Let's call it you've got a circular robot. It's got a heading, right? You've got a little Roomba running around. Okay, what might it read out?
So there can be a sensor reading for the speed, from the accelerometer.
Okay, we could do that. Yeah. So some sort of position encoder or rotation encoder. Yeah. What else? Anything?
We can also observe, I guess, if it has a camera, we can observe what the camera currently sees, the visuals.
Yeah. So I think, yeah, this is great. Let's just make it super easy and say that it gets it gets one piece of information, how far away the thing is in front of it. That's it. One beam of information. That's fine, right? So the latent state would be the description of how the robot evolves over time would be what? A model of how the robot evolves over time. F of Zn, what, it doesn't really matter. It's just whatever it is, right? How would you describe that model?
So the position at time t is velocity, like a finite forward model can use that.
Okay, fine. So there's a bunch of ways you can do that. You can write down some sort of deterministic model. You can write down a simulator of the robot. You can write down a learned model of the robot, so on and so forth, right? And for instance, the observations that you get and the noise distribution on those observations you can get by taking the robot and putting it around, so on and so forth, in lots of different places, and measuring basically the true distance or whatever and the observed distance, and you can get a distribution over, not the initial state rather, but you can get a distribution over the observation given that the robot is in some particular state. Here it's not going to be integer valued, but it's going to be in some physical location, okay? So you can, so what's the inference objective then? The inference objective would be to get the posterior distribution over where the robot is. Why would you want the posterior distribution over where the robot is? For instance, so that you can make posterior predictive distributions about where the robot will be, right? So you can, in an HMM, you can always run this forward and infer where the robot will be given noisy sensor measurements, so on and so forth. Other applications. So we did a part of speech model. So if we did part of speech model, the lazy white dog. Okay, so we have some generative model. We have something that can sample words, and this is exactly what's going to happen, right? So we have, in this particular case, f here of theta k would be, what would f and theta k be here? If we had parts of speech and words generated from parts of speech? Vasilios, you're an NLP person, you should know straight away.
Sorry, can you repeat the question?
So in the case of parts of speech, so if the latent variable is a part of speech, in other words, a discrete part of speech, and we learn from labeled data the transitions between parts of speech in, say, for instance, English, and then we try to use an HMM to infer the part of speech given a particular sentence, what would the likelihood be? Greg, you're an NLP person as well, so you might as well you can open your you can open your microphone as well.
You mean the likelihood of a sequence of parts of speech?
No, one word. What's this? Oops. What's f and theta k in the case of
emission probability?
What's an emission probability?
Probability of an observation.
It would be in this particular case, it would be a discrete distribution over the entire English language vocabulary, conditioned on it being a participle or a verb or a noun or something like that. Yeah?
Yeah.
Okay. So, and this A matrix would be the probability of transitioning from verb to verb or preposition to preposition or so on and so forth. Why might you want to do part of speech tagging? So what would the inference objective be in an HMM in which the parameters of such a model were learned and given to you? Anybody?
Oh, you can learn the
infer the infer,
you can learn the
infer the.
Oh, you can infer parts of speech. After
you can infer a distribution over parts of speech. That's correct.
Okay.
And why would you want to do that?
For other downstream tasks.
Sure, that's
to get the syntactic parse of a sentence.
There's no syntactic parser; it's just parts of speech. But yeah, you could feed it into a syntactic parser or something like that. Any other example applications of hidden Markov models before we move on?
Can I ask, is A in this sense, is it always a fixed parameter, or can it be inferred too?
So in this particular discrete case, this is the standard. This is a totally reasonable question. So I put a point here for A, but you could also, if you wanted to learn parameters, you just make that a random variable and put some prior on top of that, and then do inference. Now you have something that gives you a posterior distribution over A as well.
Can I ask another question about this?
Absolutely, please.
Is there some link between so say you were talking about Markov random fields earlier. If we're sort of, is there some link between Markov random field and a hidden Markov model? As in, like, a hidden Markov model would sort of be like a stepwise Markov random field?
No, the general relationship between Markov random fields and directed graphical models is that you can write any directed graphical model as a Markov random field by replacing the potential functions with the log conditional probability density functions. Okay, so a hidden Markov model just has this particular structure. The incredibly useful part of this structure, and we'll get to this again later on. I really just want to, this is the hardest part about any sort of like getting people up to speed and thinking about like probabilistic inference and models and graphical models and trying to get it going fast enough that we can get to probabilistic programming is somehow I have to get you to recognize that joint probability distributions are models, that you can write down joint probability distributions as graphical models, and you can think about taking applications and putting them in graphical model notation and thinking. We're going to mechanize all of the inference steps and that sort of thing. But in your head, I need you somehow to draw these kinds of pictures and be able to think from application to graphical model to program to inference task, right? That's the hard part. The hidden Markov model, the Markov property is that if you, and this is something that, Emma should go off and everybody who doesn't know this should go off and prove to themselves, is if you condition on this random variable, the future becomes conditionally independent of the past, okay? That's particularly useful, okay, for various inference algorithms, right? But again, I'm not telling you how to do inference in this yet. We won't even talk about the assembly language ways of doing inference in an HMM, but it's really about saying, okay, what is an HMM? How, what space can Z live in? What space can X live in? So on and so forth. So some more example applications of hidden Markov models, just to give you a sense. Imagine that there is some there is some latent state of a large supercomputing cluster and contention in and amongst the compute nodes. Okay, there's some transition that's learned and given to you, and these are observed, cluster node worker computation times, right? You might want to be able to predict how long the next computations will take in order to do some systems-like thing in order to cut off computations, right? I don't know where Ryan went. It's a little bit crazy that it didn't mention that, for instance, if you have an organism, right, you can observe its physical configuration, but you don't know what's going on in its brain, right? The latent state of a physical organism is there is some latent state. It's the neural activations. Those transition over time, and you produce movements. If you want to make a good prediction about what the next movement will be, a nice way to do that is to impose a model like this and condition through a hidden Markov model. The weather, the world, right? Physical systems, everything can be described by such a model, depending on what the space of X is, Z is, and how complicated the link functions are that link them together. This one's going to be even more fun. Awesome. We'll just do one example application of this. So this is latent Dirichlet allocation. And this is doing standard inference, writing a standard inference algorithm for this is the last problem in homework 1. This is the stuff that you theoretically should know before we get started with probabilistic programming, okay? This is one of the most widely cited, most recent probabilistic models. It's used everywhere. I think there's like, the original paper has something like 20,000 citations by itself. Great, okay. So what's the point? Everybody should know what a Dirichlet distribution is, what a discrete distribution is, so on and so forth. And here we'll be very, very concrete about a particular application. Here we want to take a document corpus and figure out what the latent topics are, and such that we can do document retrieval and these sorts of things. How many of you have seen LDA before? The natural language processing people and people in my group, and I don't know Emmanuel yet, but I'm gonna figure out who he is. And now that I know now that I know that he knows LDA, I can ask him tough questions. Great, cool. So let's say that we have some vocabulary. You know, sigma is all the words in English. Let's just say that that's equal, you know, the cardinality of that is 5,000, something like that, okay? Cool. And let's say we have a number of documents, okay? And what's a document? A document is a collection of words. And so we're gonna have document 1 will be, you know, 1, 17, 32, 56, 1, 4, 13. Okay, that's some sentence, just with an integer corresponding to doc 2 will be, you know, 2, 15, 32, whatever. Okay, you get the idea. Okay, so we've got the documents. Now, how would you extract so when you think graphical modeling, you think like, what do you want to do? There's two things that you want to do. You want to be able to build a distribution over objects, whatever mathematical objects you have. You want to be able to have that thing be structured such you can answer and ask and answer certain questions, so on and so forth. So we have a collection of documents, and what we want to do is we want to be able to say what topics are present. So topics. So what's a topic? Well, let's say that what topics are present in a corpus. In the corpus, what and what topics make up each document. Okay. Towards the end of being able to, for instance, compare documents and say whether or not they're similar. Now you have a problem, which is that documents have different numbers of words. And you know, if you actually want to generate a document, you have to pay attention to like word ordering and all sorts of crazy stuff like that. So we'll make a number of modeling assumptions, and we'll just talk about what this model is, and then we can talk through it. So the observed quantities are going to be the documents. This is going to be word I and document D. So this is document D, and this is word I. So again, this will be 17, 13, 3, and I equals 3. Oh, that's a terrible example, 31. So WID, where ID here is I equals 3, D equals whatever, 3 is 31. Okay, so we have a large corpus of documents consisting of words, and we're going to throw away the word ordering, which is a crazy thing to do, but that's totally fine. Okay, ZID, so we're going to generate this, so we're going to build a generative model, and we're going to describe it by a graphical model, so on and so forth. So we're going to generate these documents and the words in the documents in a particular way. We're going to say that for every word, there is a topic, okay? And that topic will be specific to the document and word, and it's going to be latent. We're not going to know what it is. Okay, great. The way we're going to generate a word is that we are going to draw a topic from a distribution over topics, and then we are going to draw a word from a discrete distribution over all the words in the vocabulary, parameterized by a distribution over those words indexed by the topics. In other words, there are going to be k different topics. K topics, let's say that's 50 topics. I don't remember how many there are in the homework. Each one of what the definition of a topic is, a distribution over words. Okay, that makes sense. So a topic, you have all the words in the vocabulary, and if the most likely words in a particular topic are like football, Brady, Super Bowl, Patriots, Buccaneers. I don't know if that makes any sense in this country. Let's go with something else. Neural networks, Jeff Hinton, Mila, vector, backprop, so on and so forth. Then you would identify that topic as being a neural network topic and the other one being a football topic, okay? So a topic is defined as just a distribution over words. We'll say there are k of them. So these are going to be very large vectors. Betas are going to be, length 5,000 vectors or something like that. Cool. And then for every document, we will have a distribution over topics. So a document that's about neural networks for predicting outcomes of American NFL games would have a mixture of words drawn from the football topic and mixtures and words drawn from the football topic. Okay, fine, cool. And in the standard sort of way, we will say that that there is a characteristic distribution over topics per document. In other words, there'll be some regularization and smoothing from that, and there'll be a regularization or typical characteristic distribution over words writ large, regardless of what topic they're in. Okay, cool. So what I have just done, and I can tell you exactly because I'm very good friends with David Bly, who's the main author on latent Dirichlet allocation, again 20,000 citations or whatever, that I can tell you that the conversation that we're having right now, and I promise if you stick with the course that by the end of the term we will be able to have this conversation very straightforwardly. I know it's like pulling teeth right now for a lot of us. This conversation that we're having right now is the conversation that took place between Andrew Ng and David Bly in a cafe in Berkeley, and they just wrote this down on a cocktail napkin, and that's how LDA was born. Okay, they said, we want to model documents. How do we build a generative model for documents? Well, let's think about topic distribution over words being topics. Let's think about a distribution over topics per document, and then for every word, let's just pick from the distribution over topics in the document, and then pick a word according to that. And that's going to be our generative model for this data. Okay. Now the question is, what do we do with this? What's the use? Okay. So let's be clear to understand that. So now what we've built up to is a relatively sophisticated graphical model, right? And I want you to think about the generative structure, and I want you to think about what you don't know, what the inference target is, and how you would use that inference target. Okay, and that's all I really want to get out of today's lecture. And it's very, very difficult without the typical mechanisms of going to the board and writing together. And that's usually what I would do. I would actually send groups to the board to talk about this. Okay, so So a Dirichlet distribution, for those of you who don't know, particularly centered on a uniform distribution, basically says a priori the distribution over topics. So theta d will live in RD, I think plus. A little more sophisticated than that, but that, whatever. Says is the distribution, again, over topics per document, okay? So again, there'll be a 50-dimensional vector per document that tells you how probable it is that every single topic, whatever those topics are, is in the document. ZID is a discrete variable for every word in a document that tells you which topic it came from. So you generate from beta k, from theta d, which is the per document distribution over topics. You generate an indicator to say word number 1 came from topic number 1, word number 2 came from topic number 3, word number 4 came from topic number 7, whatever, so on and so forth, right? Then the individual words are drawn by selecting the topic vectors, the topic probabilities, the topic discrete probabilities, according to the indicator variable drawn before. And again, a distribution over words is what a topic is. So again, this is a Dirichlet distribution, which means that it outputs the parameters of a discrete probability measure. And this Dirichlet, again, is going to be parameterized, and it's going to be regularized towards uniformity with this gamma 1 vector thing. Okay, so I ask you, because I know the answer to this, like, what are the latent variables? Let's just start with some easy stuff. What are the latent variables? All unshaded nodes, correct. And just to be perfectly clear about this, I believe actually that I should have, I believe that these will be treated as parameters in this particular work, so I should have not made these even that. So the latent variables are the thetas, the z's, and the betas, okay? Cool. What's the how would you ask which is the most similar document to the first document in your corpus? Oh, no, I love it. This is great. Exactly. So there's going to be some distribution. We'll cheat in the homework to keep it simple, but there'll be some distribution, posterior distribution of theta 1, and there'll be some posterior distribution of theta 2. Right? And we can look for, the closest in distribution between the posterior distribution of theta 1 and all other documents in the corpus. Okay. What is the posterior distribution of beta 1? words topics of each word, topics per document, words in topic. Has everybody forgotten the question? What's the posterior distribution of beta 1 given everything else? What does it mean? What is it? It's almost done. Come on. Distribution of words in topic 1 from training corpus? Yes. Is it identifiable? This is a really nasty question. No is the right answer. Good. Okay, so there's lots of supporting stuff. There's like, Murphy 2012, chapter 27, homework number 1. The original LDA paper is extremely accessible, so on and so forth. As a sort of warm-up problem to, there's a bunch of easy warm-up problems in the first homework. But the not easy homework problem in homework 1, it's not that hard, but it will force you to really understand what's going on when we're doing inference and how to reason in probabilistic models and that sort of thing. Is you will write a non-probabilistic programming sampler for latent Dirichlet allocation. It's good exercise. Cool. It would have been nice to do that one. This one we could skip. So I'll do this super quickly. So let's generate Gaussian mixture model. Let's generate clustering data. We want to do clustering. Let's do clustering. Okay. So let's say these are points in the plane. Okay. Let's pick a distribution over k classes. Let's say k equals 3. And then for every data point, let's sequentially pick, and I'll try to make this make sense, even though I'm going to change colors here just a little bit. I was going to change colors. That's fine. Let's pick some sequence of labels for 3 classes. Okay, that's what these C's will be here. These C's will be, these are the class identifiers. And then for every class, let's assume that there is a distribution in space corresponding to clusters 1, 2, and 3, which then takes these points, the cluster, it says, well, we have 4 of these points, so we draw 4 points from those clusters, and we draw 1, 2, 3, 4, 5 points from this cluster, and I don't know, 4, 5 points from the other one. Okay, so now I have described a mixture model where there's a discrete distribution over per point clusters. There is a Gaussian distribution with some per component. Sorry, I'm pointing at something you can't see. There's a discrete distribution with some prior probability of producing per data point which class it's from, given which class the data point is from, and a parameter vector of a bunch of means and covariances. You have a Gaussian distribution for each cluster with a particular mean and variance from which individual data items are drawn. We can be a little bit fancier and say that pi itself is drawn from some Dirichlet distribution, and we can be really fancy and say that the parameters of the Gaussian are given some prior as well. So in fact, we'll treat all of these things. I don't know why this black circle is missing here. We can treat all of these as parameters and do what? Unsupervised clustering, right? Unsupervised learning. So we can condition on the values of y and ask questions like, how many clusters are there? Where are the means of the clusters? How likely is it that 2 points are clustered together? So on and so forth. And we can go from there. So what's the point? It should be apparent that you definitely need to know what, common distributions are. You're going to need to know what their PDFs are, and you need to understand how to sample from those underlying distributions: Dirichlet, discrete, multinomial, multivariate, normal. We're just going to assume that you know that. We're going to assume that you know some vector algebra, so on and so forth. You might, at some point, want to think about, and we're not going to teach it, how to determine conditional independence given a graphical model. It's the Bayes-Ball algorithm or D-separation. It's not going to be critical, but it's something that you should probably read up on your own. What we've tried to do today, and it's very difficult in the Zoom COVID era, is to get you to think about probability models, graphical models. The correspondence, really all that you need to take home from today is that you write down a joint distribution, factorize it, and that factorization can be represented graphically, and you can read some stuff off of the graphical model. That's really it. But as much as I can, I want to get you to think about modeling various applications, likelihood functions, priors, structures of models, and understanding how to think in those terms and to think about how to write down probability models for various data of interest. And honestly, it would be fun, and we could probably do this. We could spend an entire course in trying to get you to think in this way. We can't do that, obviously, and it will come over time. And I virtually guarantee that if you 3 months from now, you look back at this lecture and you're like, oh my God, that was so simple. Why did we have to go through this? It's like graphical models, duh, I know what an HMM is, duh, I know what LDA is, duh, I know what a mixture model is, and I understand how to think graphically and so on and so forth. The next lectures that we'll go through will forget all of the specifics of any of these graphical models and any of these applications and thinking in this sort of a way. And we'll start talking about how to do inference in these such that we can answer various questions. Then we'll, after that, move on to how to specify graphical models in program form and write general purpose inference algorithms for models written in whatever, in a probabilistic programming language. The point being that some of you will want to actually think about various applications rather than algorithms or so on and so forth. And you should spend as much time as you can reading and thinking about how to transform your ideas and your questions into probability models in which you can answer those questions via inference. And one way of thinking about these things is it's very difficult to think in terms of the conditional probabilities that you write down as a mathematical in just a mathematical notation, but it's actually quite easy to reason and intuitive to reason when you start doing graphical modeling and you say, okay, this was generated this way and so on and so forth, and I can see what sort of dependencies there are, and eventually you'll get to understanding where the independencies come from. So that's it for today. And I look forward to seeing you on Thursday, and I'm happy to stick around to answer lots and lots of questions, which I have a feeling there might be quite a few still. Thank you. I can turn off the recording if people would rather ask questions without the recording on. Questions? None? You're welcome. Cool. In a GMM, how can we infer the number of clusters? There's a number of levels of detail to that question, but the most direct is to just say that to start with a value of k here. So pi is the distribution, is a discrete distribution over cluster identities. And if you make the dimension of pi large, then by virtue of standard regularization, so on and so forth, the number of non-zero clusters and the number of clusters that have non-zero membership will be small. So in other words, if you set k to be equal to however many data points you have, so if you set k equal to n, right, then you could potentially have n different clusters, right? But under the assumptions that you're making under the model, which is that there's things are Gaussian distributed, so on and so forth, if there is actually structure in the model such that the data is well explained by a mixture model with a small number of components, then the number of unique values of C will be small. It will be close to that number. There's a slightly more advanced story, which is to say that if you also do inference over this alpha parameter, which is how strongly you impose your prior belief that there are k clusters, then by doing inference over this alpha parameter, you will learn to concentrate on either a small number of clusters or a large number of clusters. Right? And the even more sophisticated story is that there are generative procedures that allow you to specify an infinite number of clusters and then learn in that context. And that's what this infinite Gaussian mixture model business is. It's basically a limit of a Gaussian mixture model where you take the number of components to infinity. And that is a non-parametric Bayesian model, and we will implicitly touch on that nearer the end of the term. Any more questions? Baron? Yeah? Vasilius? Tony? Adam?
Are you going to talk at all later about D-separation? You just mentioned it really quickly. I read about it in the Bayesian lecture notes. Are you going to talk about that later at all, or is that just sort of up to us?
No, is the short answer. The biggest reason for that is that when we get to it's an uncomfortable thing to jump people into probabilistic programming, because where we're going to get to are models in which that do not correspond to graphical models. And there is no generalized notion of D-separation in that case. In other words, there is no algorithm. So like in subparts of a very large infinite graph, you might be able to use D-separation to do some things. But the general case in an infinite dimensional graphical model, or a graphical model with an infinite number of nodes, you can't do, there's no Bayes-Ball algorithm. There is no algorithm that you can run to establish conditional independence, because there will be branching conditions that lead you down paths that you simply might have an observation down some path that you never ever know, and you can't even make almost sure kind of statements about conditional independence. It's like you're just screwed. So I as you're well aware, I'm still thinking about how far, well, you may or may not be aware of this, I'm thinking about how far to go down that particular path. It's like, it's the interesting bit of Prog, but it's maybe the less useful part of Prog. So unless you do simulation-based inference, which you're gonna do, so you need to know that stuff. Yeah, so I mean, the reason for some of the holes and some of the wiffly-waffly stuff is that it's really more important to get some notion of like what a model is and what what inference is and how you use inference and that sort of thing right away, because we're going to A, automate it all, and then B, we're going to move to a model family in which most of the standard reasoning that you want to do that you can do in graphical models, you just can't do it. So it's like, okay, I could spend a lot of time talking about it, but then by the end of the term, we totally forget. It's like learning all of Newtonian physics and then realizing that it's all wrong, right? It's like, and doesn't apply, right?
So graphical models and FOPL are one-to-one. There's always a mapping between the two, or is that not true?
Yeah. And
HOPL is, there exists some graphical model, but it's not defined by the start of the program, so it's kind of hard. Is that
no. So the HOPL, because there's recursion in the HOPL, in particular unbounded recursion, there is no, in general, corresponding graphical model. Like one of the conditions of a model being a graphical model is that there is a finite number of nodes. If there's an infinite number of nodes, it's no longer a graphical model.
Right.
So yeah, that's basically it. We'll get there. It'll be fun. Cool. Anything else? Awesome. See you guys.